All right. Hi, everyone. Today, we are very happy to have Pratik Rath from UCSB, Santa Barbara, virtually visit us. Hopefully one day he'll come in person. And he'll be talking about the page curve for reflected entropy. Thanks so much for accepting to give a talk, and please.
Okay, thank you so much for the invitation. As you said, hopefully it'll be in person someday, but for now we'll have to do with Zoom. So what I'd like to tell you about is some work that's been ongoing for a long while now with my collaborators, Chris Akers, Tom Faulkner, and Simon Lin. And we like to call it the page curve for reflected entropy. We're all familiar with the usual page curve of black hole information. And this is something similar where the reflected entropy is an information measure which we can compute, and it has a behavior which this cartoon is supposed to represent, where it has a phase transition at some point. And that's what I'm calling the page curve. So let me get started with some motivation. The broad motivation behind this work is it's a part of this program called It From Qubit, or in other words, trying to understand the emergence of space-time and geometry from entanglement structures in the boundary theory. The best setting in which we understand this is holography, ADS-CFT, where the first hints at something like this emergence of geometry from entanglement was the Ryu-Takanagi formula. So Ryu-Takanagi formula, just to review, is the fact that the entropy of a boundary subregion, A, which I've marked here, is given by the area of gamma A, which is the minimal extremal surface anchored to the boundary points of A. So here, this is gamma A, divided by 4g Newton. So this is some generalization of the Bekenstein-Hawking formula. And it tells us that the entanglement between the region A and A bar is computed by a geometric object, which is this area. And there have been further generalizations beyond this to understand it by including quantum corrections and so on. And it sort of all culminated in our understanding of the encoding of the bulk on the boundary theory in terms of what's called quantum error correction. So the idea of quantum error correction is that bulk operators, let's say a bulk operator here, can be reconstructed on the boundary region A, as long as it's part of the region shaded here, which is between the extremal surface and the subregion, which we call the entanglement wedge. So any operator within the entanglement wedge can be encoded on the boundary subregion. And this is, as you can see, quite redundant because any particular operator can lie in multiple entanglement wedges. And this is the fact that the encoding is in terms of a quantum error correction. So that it's a redundant encoding, which is done such that the bulk is robust to certain erasures. So for example, if you lose the information of this entire region, it doesn't matter for the purpose of reconstructing an operator within this entanglement wedge. So this is the statement of subregion duality. Now there's been a lot of work on this in the last decade or so, and we've understood this pretty well. And so the motivation here is to go beyond that and understand in a deeper way how geometry emerges from entanglement. So firstly, one problem that we still don't completely understand is so we understand the Ryu-Takanagi formula, and it's a measure of it measures the entropy, which is a good measure of bipartite entanglement. So in this setting in the previous page, there were two parties here, A and A bar. And the entropy is a good measure of the entanglement between these two. However, when we start including multiple parties, when we want to look at more fine-grained details of the boundary state, there are many more entanglement measures that have been discussed in the quantum information literature. And it's not even completely clear yet how to exactly understand the multipartite entanglement structure. So in general, we need to understand many different such entanglement measures to be able to understand the true multipartite entanglement structure. And this would hopefully help us understand some finer details of the bulk. So with just the entropy formula, we could understand extremal surfaces anchored to the boundary. And the hope is we should be able to build up every piece of the bulk geometry by using some entanglement structure. So part of this talk will be trying to talk about one such multipartite entanglement measure and try to see how it tells us something about the bulk. A second sort of theme of this talk would be understanding tensor networks. Tensor networks are these models which have helped to a large extent understand concretely how quantum error correction and subregion duality and the Ryutakinagi formula and all these features of holography work by just looking at these simple toy models. And for a long time, people had thought that we had basically exhausted what we could learn from tensor networks. But part of what I'll try to argue for today is that we still have lots more to learn from it. And in some sense, they're unreasonably effective as toy models because, as I'll try to argue, they actually capture certain non-perturbative features that show up in the gravitational path integral. And so they also know a lot about things like phase transitions and important non-perturbative effects. So I'd like to argue that we still need to understand more about tensor networks. And then a third sort of theme would be to try to understand this connection between entanglement and geometry, but now reversing the arrow. So the Ryutakinagi formula is a formula where if you have some geometry, then you can use that geometry to understand what the entanglement is. So the area computes the entanglement entropy. But somehow we'd like to reverse this arrow and let's say start from simple entanglement structures and then build up geometry. So that will be part of what I'll try to tell you about.
Pratik, can I ask you a quick question? When you say multipartite entanglement in this talk, do you mean bipartite measures for mixed states, or do you mean beyond?
Yeah, so in this talk, I'll mostly talk about just bipartite measures for mixed states. But I mean, this is a much more broad problem. Like we should really be able to understand multi-party pure state and like four-party pure states, for example.
Thank you.
But what I'll talk about here is just the reflected entropy, which will be a bipartite measure for mixed states, or you could think of it as a tripartite measure for pure states. Yeah. Okay, yeah, please feel free to ask questions and that would be good. Okay, so let me just give you an overview of what I'll talk about. So the first thing I'd like to tell you about is the key player in this talk, the reflected entropy. And so I'll first like to review certain facts about reflected entropy and how we think about it holographically. Then I'll try to discuss what page curve we're talking about here, which is this phase transition in the reflected entropy. And I'll do so particularly in a toy model of Jacquev-Teitelbaum gravity coupled to end of the world brains. This is a model that was used to understand the page curve for entanglement entropy, and it's colloquially called the West Coast model. And this model will also turn out to be a good tool to understand the reflected entropy page curve. And so I'll mostly talk about this in a lot of detail where we can solve the problem analytically. I'll then try to discuss what happens in general tensor networks. And in some sense, we'll see that the calculation done in this toy model is sort of included in these tensor networks, and they're closely related to tensor networks. And tensor networks will then help us understand slightly more broadly how to think about these this page curve of reflected entropy. I'll then switch gears and talk about sort of using these tensor networks to understand the building blocks of geometry and how the reflected entropy plays a part in our understanding of this. And finally, I'll conclude and talk about some future directions that we're thinking about. Okay, so let's get started. So firstly, let me tell you about the reflected entropy. So the reflected entropy is defined for a bipartite mixed state where we consider a density matrix on a system AB, rho AB, and we consider the canonical purification. So we think about, so we first consider the square root of this density matrix. The density matrix is an operator acting on the Hilbert space, which is a tensor product on A and B. So we think of it, so we take the square root and then think of the Hilbert space of operators. So the Hilbert space of operators on AB is isomorphic to a double copy of the Hilbert space. So we have HA tensor, its doubled copy HA star, and HB and its doubled copy HB star. And now we can interpret it as a state living in this Hilbert space, which in particular, if we trace out the factors A star and B star, gives us the density matrix rho AB. So it's a purification of the density matrix on a double copy, but it's a particularly nice one. So it's canonical in this sense. And maybe at this point, it's not that familiar, but there's a very familiar example, which we often consider in holography, which is consider the thermal state, which is this density matrix. We often consider its canonical purification, which is the thermofield double. So the thermofield double is this, this state where we consider the square root of the operator and then just change the bras to kets and think of it as a state living in a doubled Hilbert space. So this canonical purification is just a generalization of this process of going from the thermal state to the thermofield double for more general subregions. Now, the part of the motivation behind why we're studying this reflected entropy is, once we've defined this canonical purification, we define the reflected entropy between A and B to be the entropy of the region A star. So A here was the original A and A star is its double copy. This is the von Neumann entropy of A star in the state, which is the canonically purified state. This was some quantity defined in this paper by Datta and Faulkner. And we'll see that it has a nice holographic interpretation. So the reason we care about this reflected entropy is that it was proposed to have a nice holographic dual, which is the following. So we consider the entanglement wedge of, say, two intervals in ADS, A and B. And if these intervals are taken to be large enough, then we'll find that the entanglement wedge is this connected region, which is this blue shaded region. And so then we can define the entanglement wedge cross section. The entanglement wedge cross section is the minimal surface that splits the entanglement wedge into two parts, one which is homologous to A and one which is homologous to B. And the minimum such thing is what we call EW of AB. So having defined that, the proposal is that the reflected entropy of A and B is given by twice the entanglement wedge cross section divided by the familiar factor of 4G Newton. Sorry, should have not been here. Okay, good. So this is a nice holographic.
Excuse me, may I ask you something?
Yeah.
Your definition depended on the density matrix rho AB from the previous slide.
Yes.
Where does it show up in this holographic version?
In the holographic version, the place it showed up is that we're considering the entanglement wedge of AB. So this blue region you should think of as the bulk dual of the information on AB. So if you had access to the density matrix on AB, then you would have access to this blue bulk region. And then we're considering the cross section that splits that particular cross section, that particular entanglement wedge.
So, for example, for thermal rho AB, I would be looking at a black hole in the bulk, no?
Yeah, you can think of it that way. Yeah. So if we take the familiar example of the thermal state, then
for example, yes.
Yeah, you can like think of say a black hole with this boundary, and then say A is one part of it and B is another part of it. And then it would be the thermofield. There would be a two-sided black hole, the canonical purification.
But in principle, in general, I have to know the bulk dual to a given density matrix.
Yes, we're starting with that. Yes.
All right, thank you.
Good. So this, before I say anything else, let me just tell you that the reflected entropy was pretty much defined in this context, and there has been very little study of it from a quantum information perspective. And so we still don't know much about it in a universal setting, but we do understand a lot of it assuming this holographic proposal. So if we assume this holographic proposal that the reflected entropy is computed by twice the entanglement wedge cross section, then one can show that the reflected entropy is a good measure of correlations between A and B. And it satisfies all the properties you need from a correlation measure. So it's some measure of entanglement between A and B, which could in general be in a mixed state. So it's a nice generalization of the Ryu-Takayanagi formula. In the Ryu-Takayanagi formula, we had a formula which would tell us about the bipartite entanglement between in a pure state, whereas which was computed by a different area, something like this area. Whereas now we have a measure which computes the bipartite entanglement in a mixed state, and it's given by this area. So it's a nice sort of generalization of that. Okay, so now why should this be true? So let me just give you a brief motivation. Yes?
Can I ask a question? So
Yep.
I'm under the impression that the reason people never studied this measure, as opposed to entanglement of purification, which was a well-studied measure in quantum information, is that there, to my understanding, is that there is no proof of monotonicity of this quantity or the data processing for this quantity. What's the status of that? Do we have counterexamples? Is that correct?
So good. So there's no counterexample. More so, like as I was saying, like if we assume the holographic proposal, then using the holographic proposal, we can prove that it satisfies the data processing inequality. Similar to how we would prove strong subadditivity using the Ryu-Takayanagi formula. But you could still ask, like, are there violations of this in more general settings? And to my knowledge, there's no counterexample. At some point, I was trying to look for counterexamples and I never found any. And I think some condensed matter people have also looked at this and they also haven't found any such counterexamples. It's possible that maybe there might exist some small counterexample. Like we like to think of it as similar to the additivity conjecture. Like you might find some small counterexample, but maybe largely it's kind of true. So that's the current status of it. Like it's not been proved that it's a measure of correlations in the sense that we don't know if it satisfies data processing, but at least in these settings where we think about it, it seems to work.
Okay, thank you. So you're saying that assuming geometry, you could prove the same way that you would prove strong subadditivity.
Yes.
Thank you.
Yep. That, by the way, is a good open question to be studied. I mean, I think we should be able to answer this question, but no one has made progress on it. Okay, so now let me just try to briefly motivate why you should believe this proposal. And the idea is pretty simple. One would like to first consider this canonically purified state, square root of rho AB, and look at the geometry that's dual to this state. Once we can find such a plausible geometry, then the entropy is just computed by the Ryu-Takayanagi formula, so we can just use that. So what sort of geometry should be dual to this canonically purified state? Well, firstly, we know that the information contained in the density matrix on AB was exactly that of the entanglement wedge of AB. So what we can do is consider a double copy of this entanglement wedge. So we take the geometry here, this blue patch, and glue it to a second copy of this at the extremal surface gamma AB. Now, because it's an extremal surface, this is an allowed thing. You can solve the constraint equations by gluing two pieces of data at this extremal surface. So it's valid initial data, and then you can evolve the geometry into the future and see what it looks like more generally. But since we're only interested about this particular slice, the geometry is basically that. It's two copies of that blue region glued together to form some sort of a cylinder, where A and its double copy is on one side and B and its double copy is on the other side. This is an example of, sorry, go ahead. You had a question.
Just a quick question about what you just said. So if this were not an extremal surface, then you would have needed some matter to support this geometry.
Yes.
That's the statement. Otherwise, you wouldn't satisfy the Hamilton constraint, right?
Exactly. That's right.
If if you do add matter, you
Yeah.
could like put a brain or something on this RT surface. Can you make this work? Can you sew it for an arbitrary surface?
Yeah, you could if you source it appropriately, but yeah. So for example, like I mean, we know that the HRT formula is not exactly correct. Like there are corrections to it. For example, we would look for quantum extremal surfaces, and quantum extremal surfaces wouldn't be extremal. They'll have some term coming from the quantum corrections. So in that case, we still expect that you have some sort of double geometry like this, but there would be a source from the matter term. And that matter term would be exactly such that it makes you satisfy the constraint equations. But this hasn't been worked out in any detail.
Thank you.
Yeah. Okay. So this gluing procedure is sort of a part of what was discussed in this paper by Engelhardt and Wall, where they considered the CPT gluing together a CPT conjugate of a geometry at the extremal surface. So this is just one such example. And this geometry has all the right flavors. It has this nice symmetry between AB and A prime B prime. It also has the feature that it's a purification, so the entanglement wedge of AB remains unchanged, and so on. So a lot of arguments were made in the paper by Datta and Faulkner to motivate that this is the right way to think about this state. And once you think about it this way, then the entropy of AA prime is just given by the Ryutakinagi formula, which says that you look for the minimal extremal surface homologous to it. And then from the previous picture, we see that the entanglement wedge cross section and its doubled copy, which we see here, is the correct surface that does so. So two copies of the entanglement wedge cross section are exactly what the Ryutakinagi surface for AA prime looks like. And hence the entropy of AA prime, which was the reflected entropy, is just given by twice the entanglement wedge cross section. So this is sort of the brief motivation behind why you should trust this, this proposal. Okay. Good. So having told you about reflected entropy, let me...
Can I ask a quick question?
Yeah.
I think
Yes,
you wrote it on your slides, but you removed it. So this argument you gave seems like an proof. Why did people use the replica trick to prove this? I mean, why was there a need for another argument? This to me seems like a proof.
I think it's well, I think, okay, so in what I'm going to say ahead, we'll see that this is a little subtle. So for example, another, basically, so this is basically correct as long as you're away from phase transitions, but near phase transitions, there can be subtleties, and you see that in the replica trick. So the replica trick is some more robust way in which we can check that this is true. And this argument is basically correct as long as you're far from phase transitions.
Sorry, what phase transition? You mean the RT snapping?
Yeah, from the RT snapping.
But in that case, if you don't have a connected region, then your reflected entropy is 0, right?
Yeah, so what ends up happening is that near the place where the RT snapping happens, you sort of get two geometries. There's one geometry which looks like this, and there's another geometry which will be sort of two disconnected copies of AA prime and BB prime.
Right.
And the real state, which is the canonically purified state, is some sort of superposition over those.
Oh, I see.
And we'll see that in the toy models, like more explicitly. But apart from that, like what you're saying is correct. Like this should basically be thought of as a proof as long as you're far from phase transitions.
Thanks.
So the replica analysis sort of helps understand the near phase transition stuff. Yep. Okay, good. So now having talked about the reflected entropy, let's discuss the page curve. Well, that's pretty straightforward, as Nima was just asking. So if we just consider sort of two intervals in ADS, then as you make, for small sizes of these intervals, the RT surface is disconnected, is just here. And then if you make this larger, eventually it becomes connected, such as this. In the disconnected phase, there's no cross-section because you don't need anything extra to split the regions which are already disconnected. Whereas when it's connected, then you have this blue surface which splits it. In the disconnected phase, the entanglement wedge cross-section is 0. So the reflected entropy is just 0 at leading order in G Newton. Whereas as soon as we hit the phase transition, the entanglement wedge cross-section jumps to a finite non-zero value. So there's a sudden jump in the entanglement wedge cross-section, or effectively the reflected entropy, from 0 to non-zero. This is different from what happens in the entanglement entropy phase transition, where it's continuous but non-differentiable. Here, the transition is such that the value itself jumps. So this is sort of a unique feature to this reflected entropy. And so this is the page curve that we'd like to analyze. So this particular jump where the entanglement wedge itself changes and the reflected entropy jumps from 0 to non-zero.
Sorry,
Okay.
can you repeat again the statement you meant? This is as opposed to the
So what I meant was if you just look at the reflected entropy, it'll just follow something like it'll go from here to a finite value and then change. Whereas for say something like the mutual information would have the behavior where it's 0 and then it grows from here. So it has a phase transition, but it's still continuous.
I see. Thank you.
Yeah. Yep. Okay, good. So this was the page curve. Now let's talk about all of this in more detail in a specific model. So we'll talk about this model called the West Coast model. It was defined by these authors, Pennington, Schenker, Stanford, and Yang, for the purpose of computing the page curve for black hole entropy. And the model is pretty simple. It has a few parameters, which are these S naught and mu. And what this is it's a model where we have JT gravity. So this is the JT gravity action. There's a topological term, and there's a term which dictates the dynamics of the dilaton. And it's coupled to entangle to these end of the world branes, which have this action. So the action is just proportional to the length, and the mass term or the tension is just this parameter mu. And this is the total action. The solutions to this action take the following form. In Euclidean, the solutions look like the following. So we have solutions like this, where you have an asymptotic boundary, where we fix some boundary conditions for JT gravity. And then there's an end of the world brane, which is denoted in blue here. And so you get some sort of disk-like solution. When we analytically continue this, so let's say we just take the data on this slice and then analytically continue into Lorentzian, then you get the data here, and the solution looks like this, where now you have an asymptotic boundary here. There's a horizon, and the end of the world brane lies behind the horizon. So this is what this model looks like, and the solutions look like. Okay. Now further, we'll consider that the branes, they don't have any dynamics except for the fact that they have this action given by the mass, but they do have some internal flavors. So the brane will have these two kinds of sub flavors labeled by this orange line and the green line. And what we will do is consider a state where there's a black hole with these end of the world branes behind the horizon, which is entangled with some auxiliary reference system, which we can think of as the early radiation. So you can think of this as a model of where the black hole has started evaporating, and you capture some of the radiation, and that's entangled with these interior modes. So we consider an auxiliary system which has two parts. There's an R1 and an R2. R1 has these labels I, which are entangled with the green subflavors, and R2 has these labels J, which are entangled with the orange subflavors. This is a slight generalization of what they did there. We just want these two different R1 and R2 to have a non-trivial reflected entropy to compute. But in general, all this is some, you should just think about these colors as noting some internal flavor index of the branes. And then given that, we're considering this particular state. So we're considering a state where the black hole and radiation are entangled, and they're maximally entangled. So they're entangled such that the psi ij, which is the black hole state with internal indices I and j, is entangled with the state of the radiation of I and j. Okay. So we'll consider this specific state. How do we now compute the reflected entropy? So first, let's discuss how we compute overlaps between these states. So the overlap between psi I1J1 and psi I2J2, which are states of the black hole, is essentially done by computing the path integral. So we have boundary conditions where we fix some asymptotic boundary conditions at infinity. And then we have these labels I1, I2, J1, and J2, which label these indices of the end of the world brane. This sets the boundary conditions. And then the way we compute this is by filling in the asymptotic boundary conditions with some saddles or with some geometries. And we integrate over all of these geometries. So for example, when we compute this overlap, the only geometry we have is this disk-like geometry. Also, in general, in JT gravity, we consider a genus expansion where we have higher genus surfaces and so on. In this talk, we're only going to be discussing, we're going to suppress all of those higher genuses. One way to think about it is we take S0 to be really large, and all those higher terms are suppressed by powers of e to the S0. So we'll only ever talk about the lowest genus solutions. So in this particular case, the only such thing is the disk. Now we'd like to compute the reflected entropy of R1 and R2. So we can think of R1 as A and R2 as B, and we want to compute the reflected entropy between them. So the first step to do so is look at the density matrix. The density matrix on R1 and R2 is given by just using this formula. It has these matrix elements which are given by overlaps of the black hole density matrix with specific labels. Okay, and as we saw, this matrix element is computed by these boundary conditions. Good. Now, what we'd like to do is compute the square root of this density matrix. The square root of this density matrix is hard to do.
Sorry, Pratik, can I ask you a quick question about last slide?
Yeah.
So if you don't have matter fields in the bulk, it's just like a gravitational calculation, shouldn't this overlap of psi ij's be just proportional to delta?
That's right. So in this geometry, for example, like we just have so the end of the world brane links the two ends, and so there is it's only non-zero if I1 is the same as I2 for this particular saddle. I mean, so this thing is really proportional to delta I1 I2 delta J1 J2. Right.
So okay, I see.
Yeah.
So you're going to consider a more non-trivial setup, I imagine.
Yeah, I mean, this thing will, I mean, so it depends on the quantity you're computing. There will end up being like corrections to that. For example, when people consider like norm square of this thing, then you start getting terms where you have wormholes.
Yes,
so you won't need something like that. So yeah, so those will become important.
Thanks.
Yeah. Good. Okay, so in order to compute this square root, the trick we'll employ is to consider the replica trick. So we can first consider powers of this density matrix, and so if we want to compute trace of row R1 R2 to the n, so here let's say n equals 4, then we'll just take the matrix elements that we computed. Each of them was computed by one of these diagrams, and glue them together cyclically to implement this matrix multiplication, and then trace over it. So this sets the boundary condition for computing trace row to the n. And then we're told to fill this in with geometries and integrate over them. And so what we'll end up with is a sum over topologies of such form. Since we've already neglected higher genus corrections, we'll just draw these disk-like diagrams. And further, we could have, in general, solutions or geometries which sort of anchor on these two separately and these two boundaries separately. But these would cross in the bulk, and one can show that these are suppressed by powers of k being the number of indices. So we'll work in a limit where K is also large. And so you can suppress all of those non-planar diagrams. So what we'll be left with is just these planar diagrams. So here is an example where we have, the value of this particular diagram would be given by Z1 squared. So Z1 is basically the path integral over JT gravity with one asymptotic boundary. So there's two of these times a factor of Z2, which is the path integral with two asymptotic boundaries. And then there's some index loop contraction. So there's two of these loops. There's one here and there's one here, both of which provide a factor of K1, K2. So this is an example of one such geometry. And in general, we'll have to sum over all such topologies, so different ways of it connecting and so on. It's even after doing this, even after restricting to planar diagrams, it's difficult to directly sum over all of these topologies. So we'll employ a trick to do this sum over saddles. So the way one does this is to consider the resolvent trick. So in the end, we're going to end up doing something similar for the reflected entropy. So let me just first explain how we do this for the entanglement entropy, and then the story will be quite similar for the reflected entropy. So we first consider this resolvent Rij, which is defined by the following. It's basically the generating function of rho to the n. So we have a sum over rho to the n with these factors of 1 over lambda to the n plus 1. And it essentially defines this identity over lambda minus rho. And remember that these I indices basically talk about are basically the I1, J1 that we talked about before. And similarly, J indices are the I2, J2 that we talked about. So these are the labels on R1 and R2. So diagrammatically, what this looks like is there's firstly a delta Ij term. So this delta Ij is just this product of this green line and this orange line, which is proportional to delta I1, I2, delta J1, J2. And then there are more terms. So there are terms which have these rho to the n's, which from the previous slide is just the first term would have one boundary, which is just a single power of rho. Then we have terms with n equals 2. So there are two boundaries, but they could be either disconnected or connected, and so on. So there's many such terms, and we've sort of arranged them by the power of n here. Now, a trick to do this is to do the sum in a different way. So instead of focusing on the number of asymptotic boundaries, we'll focus on what the first connected component is doing. So if we re-express this sum in the following way, the first term is as it is. In the second term, we have one asymptotic boundary, which has just a single connected component. So it's just a disk, followed by arbitrarily many disconnected components. But arbitrarily many components was anyway what the resolvent was supposed to compute. And so we can just add in this R to signify that there are arbitrarily many components beyond this. Similarly, we can consider that the first connected component has two asymptotic boundaries, these two, which gets connected by this wormhole. And between them, and also here, we can consider arbitrary products of more and more asymptotic boundaries and geometries. So this is now the same sum as we had before, but we've just re-expressed it in terms of the number of asymptotic boundaries of the first connected component. Okay. Good. So now we can just consider this sum. This sum is quite simple. And once we consider the trace of Rij, which we define to be this R, then from the delta Ij term, we just get a factor of K, which is just the product K1 and K2. And there's a sum over n, which here signifies the number of asymptotic boundaries of the first connected component with Zn. And then there are powers of R. So these powers of R show up there. So you get some simple sum. And then by using a sort of integral representation of these Zn, which were these n boundary partition functions, which depends on the density of states in JT gravity, and it has a corresponding Boltzmann weight. We can think of it that way. The dependence on n becomes pretty simple. So the sum just becomes a geometric sum, and you end up getting an equation of this form. The key point of this equation is we've expressed R self-consistently in terms of R. So there's an equation for R, which we can usually call the Schwinger-Dyson equation, where you're solving for R in terms of R. And so you can self-consistently solve for this. This was done in the original paper, and they found what the spectrum looks like. And there are two interesting cases. You can consider boundary conditions with fixed energy, or the microcanonical ensemble, or you can consider boundary conditions at fixed temperature, which is the canonical ensemble. In the microcanonical ensemble, one ends up getting a density of states, which is just a small peak. So it's sharply peaked at some point. And in the canonical ensemble, one ends up getting a more interesting spectrum, which is what they called a cutoff thermal spectrum. So it's a thermal spectrum which has been cut off at some value and shifted. That won't be so important, but essentially the point is that in both of these cases, the spectrum can be analyzed. And this, remember, is the entanglement spectrum. And this will play an important role in understanding the reflected entropy.
Can I ask a quick question? Can you go a few slides back when we had these these gravitational integrals? Yeah. So here in this pictures, you have in your equation you have R of lambda.
Yes.
But in your pictures you have R's, right? So what is the lambda here?
This R of lambda, I mean, R is always a function of lambda. So we defined R as a function of lambda because it had this expression, and R here is the same thing. So these R's are still functions of lambda. I've just left that implicit.
But can you go one slide back?
Yes.
So here, I guess this expression is correct for lambda less than 1. Is that right?
Yeah, we're defining it. Yeah, for lambda greater than 1, I think. We're defining this as expansion in powers of 1 over lambda. So we want large lambda for this to converge. But eventually what we'll do is analytically continue it to values which are less than 1. And that's maybe what you're saying. Like we want to define the density, for the spectrum of eigenvalues, and all the eigenvalues are less than 1.
Because I mean, the eigenvalues are the points where lambda minus rho would not be invertible. So I imagine this thing is analytically well defined everywhere except for the interval between 0 and 1.
Exactly. I mean, in general, it can have poles in 0 to 1, or it could have branch cuts.
Yeah.
But yeah, they'll all be, for a well-defined density matrix, they'll all be between 0 and 1. Yeah.
Thank you.
Yes. And that's what we find here. So here, I mean, this spectrum is basically that. So these shaded regions are exactly where the branch cuts lie. So these regions are the branch cuts in R, and hence we get some density of states there.
Oh, sorry. So the equation in the box is actually the requirement for the analyticity. So that's yeah, I see. I understand now what's going on. If that's the only branch cut, that you will have to have this equation.
Yes.
I see. Thank you.
Yeah, thanks for that. Okay, good. So now we can move on to the reflected entropy. So we're going to do something very similar to what we did before. And so we want to consider the square root state, but we don't know how to take the square root. So we'll consider rho to the m over 2 when it's even. This can be done by the same thing that we did before, just taking multiple copies of the density matrix. Once we do that, we'll try to extract the R1 star spectrum using the resolvent trick, and then analytically continue m to 1. This will end up giving us the reflected entropy. So that's the way we'll go about this. Before saying that, let me just say what we should expect. So the parameters in this problem were basically the black hole entropy, which was fixed by S0 and perhaps the black hole temperature beta, and K, which was the number of flavors. Now, depending on how these compete with each other, one can either be in the disconnected phase or the connected phase in the context of entanglement entropy. The disconnected phase is where the radiation does not have an island. So the entanglement wedge of the black hole is this whole region. And in that case, you can think of the entanglement wedge of the radiation as being disconnected. There's no connection. There's no geometric connection between the entanglement wedge of R1, R2. So we expect the answer SR equals 0, which was what we got in the holographic case in general. Whereas when we're in a connected phase, in the connected phase, the radiation has an island. So the interior region here is part of the entanglement wedge of R1, R2. And now there's a non-trivial geometric connection between them. So one can think of these being coupled to R1, R2. There's some entanglement between the branes and R1 and R2. And the only possible cross sections in this picture are either to cut the leg at R2 or the leg at R1. There's no other way to split this entanglement wedge such that it becomes homologous to R1 and R2 separately. If we cut this leg, the entanglement cost is log K1. And if we cut this leg, we have log K2. So this is sort of the analog of the entanglement wedge cross section in this picture. You can think of it as a quantum generalization of the holographic proposal. And then the proposal was that the reflected entropy is just twice this minimal entanglement wedge cross section. So we minimize over these two possibilities, and twice that is the reflected entropy. This is the expected answer. Okay. Okay, good. So let's just go through the diagrammatics quickly. First, we want to consider the state rho to the m over 2. This is done in.
I apologize. Sorry. Do you mind? I think it was a little bit too quick for me. So
yeah,
there are two phases. The disconnected phase is the. Let's see. So it's the one that.
So the disconnected phase is where the RT surface, so to say, for R1, R2 is just this one, where it just cuts the legs of R1 and R2. Where R1 and R2 are entangled with the brane. So you just cut it open here.
Oh, sorry, I just understood. But R1 and R2 are like, so you take early radiation, split it into two parts, and you're talking about the entanglement wedge of early radiation. Okay, I see. In a sense, mutual information between R1 R2.
Yeah, you could say that. Yeah.
I see. Thank you.
Yeah.
Thank you.
Yeah. Okay. Good. So good. So we now have, okay, so we have these m over 2 boundaries, asymptotic boundaries glued together cyclically. And this prepares this density matrix for us. As a shorthand, we'll just take these m over 2 boundaries and represent them by this purple line here. You should remember that it contains these m over 2 asymptotic boundaries. In the end, everything will be analytic in M, so we'll be able to analytically continue that trivially without doing any other new tricks. So for all purposes, we'll just think of this purple line as some simple notation. And further, there's one basic ingredient, which is we have this step where we take the operator, which is the density matrix, and interpret it as a state. So we take the matrix and then just flip the bra and ket. So here, that's what we're doing. This operation gamma is a step where all we're doing is taking the green label from the right to the left and the orange label from the left to the right. So this is basically the same thing, but we're just thinking of it now as a state on R1, R1 star and R2, R2 star. Okay. So once we have that, we can look at what the density matrix on R1, R1 star is. Well, in this state, what we'd like to do is just trace out the R2 and R2 star degrees of freedom. So we take two copies of this picture, which are this and this, and then glue them together on these labels. So we trace out the orange labels. This leads to a density matrix on R1, R1 star. This is the ket and this is the bra. Okay, so this diagrammatic picture prepares for us the density matrix on R1, R1 star. And in the end, our goal is to compute the entropy of this, or more generally, the spectrum of rho R1, R1 star. And so we'll use the resolvent trick now using this diagrammatic picture. Okay.
Sorry, I'm a little bit confused. So your last equation, the left-hand side doesn't have an M.
Oh, this one, yeah. I mean, it does have an M. So I'm keeping M implicit here. I mean, the purple boundary represents M over 2 asymptotic boundaries. In the end, we'll be analytically continuing M, but everything depends on M. Like there's an M dependence here and also here, everywhere.
Yeah, okay, so good, thank you.
Yeah. But I just don't want to confuse you with this. I mean, this is not the mth power of the density matrix. It's just the density matrix you get from rho to the m over 2. That's the only difference.
Correct.
Okay, good. So now what's the resolvent trick telling us to do? So now we consider a slightly different resolvent trick, which will be useful in this case, where we consider this rho to the m over 2 as the off-diagonal elements of a matrix. So we take these on the off-diagonal elements and then take arbitrary powers of this and sum over this. So it's the generating function of this matrix. So now let's look at the diagonal terms. So the diagonal terms will come from multiplying these off-diagonal terms with each other, which we saw earlier. So we saw that multiplying rho to the gamma dagger with rho to the gamma was this picture, which gave us rho R1 star. So what we'll get on the diagonal terms are rho R1 star to the nth power. So for all the even terms here, we'll end up getting these diagonal terms. And there'll be off diagonal terms, which are basically coming from odd powers of these. But those won't be important for us. In the end, all we want to do is the spectrum of rho R1 star. So we'll only focus on this component. This matrix resolvent is a useful trick for it, but in the end, all we care about is the resolvent, which is just the first component traced over R1 star. So it's just this component that we care about. Okay. All right. So now let's look at how we compute this resolvent. It's very similar to before. We have the same kinds of terms. And so we're interested in this 1 component. And so we look at the diagrams corresponding to that. So there's one diagram here, which is just the first term, which was the delta ij term. And then there's a term which is proportional to rho. And then there'll be higher powers of rho and so on. Now, there are qualitatively two kinds of diagrams that will show up here. There are diagrams which will be disconnected between these two purple boundaries, and there'll be those which are connected. So let's look at it in some more detail. Let me remember that these purple lines represented m over 2 asymptotic boundaries. So let's take m equals 4 again and look at both of these diagrams in a little more detail, this one and this one. The disconnected one itself has m over 2 asymptotic boundaries here and m over 2 asymptotic boundaries here. When we say disconnected, we just mean that there's no geometry crossing this middle line. So you can have, say, a 2 boundary saddle here and two 1 boundary saddles here, for example. The important point will be that as long as they're disconnected, what we care about is the pattern of the green indices. So the green indices here, you can see follow this pattern and this pattern. So in the end, they're proportional just to this projector. So remember that these ends were R1 and R1 star, and this is R1 and R1 star bra. And so what we see is that this thing is just proportional to a state. It's a state which projects the index on R1 to be the same as the index on R2 on R1 star. So it's just an entangled state between R1 and R1 star, and the density matrix is pure. That's the interpretation of this kind of diagram. On the other hand, we can have these connected diagrams. These connected diagrams will have some general filling in geometries, but important point is that they're connected across this middle line. If they're connected across the middle line, we can look at the green labels again. Now they follow this pattern, which we can straighten out to this form. This is now a maximally mixed density matrix. So if we look at the density matrix of R1 star, it's maximally mixed. So there's a delta ij between R1 bra and ket, and similarly R1 star bra and ket. So if we were to compute the entropy, this would be a maximally mixed density matrix, which would give the answer log 2 log K1. Okay. So essential point here is that there are qualitatively two kinds of diagrams. Like the full resolvent can be divided into these two kinds of diagrams, one which is proportional to the projector and one which is proportional to the maximally mixed state. And this will sort of be the key point. Okay. So now how do you resum all of this? Well, what we can do is think of the connected part of R. So this is similar to what we do in quantum field theory. Instead of computing the propagator, we look at the 1 pi effective contribution. So this is something like that, where we consider this F to be the connected part, and then R is just given by a sum over powers of F. So it's just given by this 1 over lambda minus F. This is just some convenience. You couldn't do the sum without this. F will have the same kinds of terms. There'll be these connected terms and disconnected terms, some of which will be proportional to the projector and some of which will be proportional to the maximally mixed state. Now, once we take care of that, what we end up getting is a Schwinger-Dyson equation. We had R, which we expressed in terms of F, but F itself is a function of R because we have this factor of R, which is inserted here. So it's again some self-consistency equation, the details of which it's a little hard to go through in short time, but we can solve this self-consistently. And there's a small assumption that we need to make in order to solve this. We need to do this perturbatively, and we keep only a few terms in this expansion. We can check that the higher terms are mostly suppressed, and also that this works out well with the numeric. So we can numerically test this and see that it works well. And so we believe that this truncation of higher order terms is good, but it's still an assumption. So let me just lay that out. With this assumption, we can solve this equation. Yeah.
What is the suppression in?
Yeah, it's not really so. The contributions that come from those higher terms. So here we have these what I call k equals 1 and k equals 2. K is just the size of this this diagram. So here there are two purple boundaries that it connects. That's what k is. It's not obvious that any of these higher terms should be suppressed as such, but they end up giving contributions to the spectrum that are either suppressed that are suppressed in k. Not this k, but in the size of the Hilbert space. So k was the number of flavors, k1 and k2 were the number of flavors. All the contributions that come from these higher terms end up being suppressed in that.
I see. Thank you.
Yeah, it's not obvious, and it's actually even hard to prove. So we don't have a proof for this, but this seems to work pretty well. Okay, so having said that, now let me give you the summaries. So maybe the details of the resolvent were hard to understand, but the result is pretty simple. So the spectrum that we end up getting, and this is the spectrum on R1, R1 star, is pretty simple. So it has this form where there's a mound of eigenvalues, which has either it has the min of k1 squared or k2 squared eigenvalues with some weight. This corresponds to the terms which came from this maximally mixed state. So this maximally mixed state gives rise to some entropy, and that's because of these eigenvalues here. On the other hand, there was a projector, and this projector is a single pole. So in the spectrum, there'll be a single pole with some weight that gives you this term. And the spectrum is a combination of these two. So you can think of this as two super selection sectors. And the interpretation of this is there's some probability of being in the connected phase, and there's some probability of being in the disconnected phase. As you tune the parameters, the relative weights of these two super selection sectors will change. And eventually, so if when you're far in the disconnected phase, this pole dominates. and the pole naturally gives you a reflected entropy of 0. On the other hand, when you're in the connected phase, this mound dominates, and this mound gives you an answer that's the answer you would expect in the connected phase. In the middle, they interpolate. So the canonically purified state can be thought of as a superposition between these two. And so it nicely interpolates from one side to the other with their relative weights changing. These weights are computable. They essentially depend, after doing all of this analytic continuation and so on, they end up depending on the half-Renyi entropy. And this is something that's computable from the previous calculation. So first we showed you how to compute the entanglement spectrum. Using that, you can compute the half-Renyi entropy. And this has some sort of nice interpretation. This is also the probability that shows up in Pett's reconstruction. And it has this interpretation of the probability of being before the phase transition. So the weight of this pole has this interpretation of being, you can think of it as the probability of not having undergone the phase transition. And hence it's in the disconnected phase. So this.
Sorry, I'm very confused about this.
Yeah.
What is the probability? Is trace of square root rho?
Yeah, so it's good. This probability is just some interpretation that we're giving it. So if you look at the Pett's map calculation that was done in the West Coast model paper, they found that there are similar terms. So when you try to do the Pett's map reconstruction, there's a term which corresponds to being in the having the island and being able to reconstruct the operator, and that takes essentially this form. Whereas the other thing is like 1 minus that. This pre-page probability is just some interpretation we're giving it. I mean, from this expression, it's not at all obvious that this should have any interpretation as a probability.
But is that number even between 0 and 1?
It is. Yeah, you can check that it's between 0 and 1.
But I mean,
so the important,
because trace of rho. Oh yeah, you're normalizing by k. Okay.
We're normalizing by k, and k is also the rank of the density matrix. So it's always
yeah, for sure. I mean, it's a little bit of an ad hoc normalization. To me, it looks like a half. Yeah, it's like a fidelity kind of thingy.
It's a fidelity kind of thing. Yeah, I mean, this normalization is not ad hoc because this comes from the calculation. I mean, in the calculation, we end up getting this spectrum, which has these numbers in it. That number just turns out to be this. The interpretation as a probability is something we're putting in. But I mean, once you have the spectrum, you can sort of think of these two sectors, and then the probability is the natural thing to it.
But this is, I mean, I guess, correct me if I'm wrong, but this is not really spectrum of any particular density matrix of a quantum system. This is what gravity suggests as, I mean, the thing that's somewhat confusing is that even if you accept gravity as an ensemble of theories, then you would still have a density matrix.
Yes.
So which would say, is there a density matrix whose spectrum is this or not? I'm a little confused.
No, there isn't, because this is continuous. So this the spectrum you get here is there's a branch cut instead of like a sum over poles or something. There's really a branch cut, and that's because of this fact that you said. There's an ensemble averaging which is taking place, and so you're getting a continuous spectrum. But the point is that even if you picked a single density matrix, the answer is pretty similar to this, but it's not going to be exactly this.
But I guess what I was saying is that an ensemble of density matrices is a density matrix. That's what I was saying.
Well, I mean, that's true, but I don't know if you can. So when you say density matrix, you just mean it has trace 1 and it's positive, right?
Correct. I mean,
yeah, I mean, if maybe sometimes we also want to say that it has a. I mean, this is a finite dimensional Hilbert space, so you'd probably want to say that it has the spectrum is a sum over poles. Which would typically be true for a finite dimensional density matrix. That won't be true here. But the trace is 1 and it's positive. That's true.
Thank you.
Yeah. Good. So I realized that I'm actually out of time. This was, yeah. Okay, let me just quickly tell you about this. Yeah. So as I said, the weight of the pole shifts as you move across the phase transition. It's 1 near the disconnected phase, and then it drops to 0 near the connected phase. So you end up getting a reflected entropy, which has exactly this feature of the jump. So in the semi-classical limit, you get a discontinuity in the reflected entropy, and it jumps from 0 to non-zero very fast near the phase transition. Now, we did this calculation in both the microcanonical and canonical ensemble, and you find qualitatively similar behavior, but because the canonical ensemble has these thermal fluctuations, what ends up happening is the entanglement wedge transition itself is spread out over a region of order 1 over square root g in this log k. So it's a slightly wider transition. But apart from that, it's pretty similar. This feature of spreading out of the phase transition is also visible in the page curve of entanglement entropy itself. So this is quite expected, and it's nice that it matches up very nicely. So whatever we expected from the holographic proposal seems to work exactly correctly. The answer that we end up getting is this thing which has this interpretation of 2 different sectors, as I said. Before, there's an area term which either takes 0 in the disconnected phase or like 2 log k1 in the connected phase, and we have the probabilistic mixture over those. And there's a Shannon term which comes from the mixing of these 2. So that's the answer we get. So in a way, in the soy model, we can like see that the holographic proposal is correct. And it has this nice interpretation where there were these 2 saddles, as you were asking earlier. There were these 2 saddles which you could draw. One was the connected saddle and one was the disconnected saddle. And they both exist at all points in space. It's just that their weights change. And so far from the phase transition, the argument where you consider this double geometry was exactly correct. But near phase transitions, you need to take into account the relative weights between these 2. Okay, how much time can I take? Like, otherwise I can stop here at this point.
Well, I think you can continue, but if people want to leave, they can leave. I mean, if there is a natural ending point for everybody, you could choose that point, and then we can continue chatting and having it like a little bit more informal if you have time.
Yeah, I mean, I'm fine with that, actually. I mean, this is sort of a natural stopping point. I mean, I haven't talked about tensor networks at all. I think I'm good with this. We can stop here and we can discuss more. I can tell you more about it.
Okay, wonderful. Then why don't we just thank you first. Thank you so much for the great talk. And let's ask for a few questions. And then once the questions are done, we could continue a little bit longer if you would like.
Yeah.
I would definitely love to hear more. But okay, so are there questions for Pratik?
I just want to say thank you for the talk, but I have to leave. So nice to meet you. And thank you.
Thank you so much.
Any questions? I guess there were a lot of questions during the talk. That's why I sort of ran out of time. So if there are no questions, maybe we can continue a little bit. How much time would you like to have?
I'm okay with like another 15 minutes, maybe.
Yeah, that would be wonderful. Thank you so much. I mean, people should feel free to leave if they want.
Sure.
Okay.
Okay, good. So now let me just briefly tell you about tensor networks, like what we can say about those. So in the tensor networks, in a previous paper with Chris Akers, we were arguing that there's a very similar picture you can draw for the canonical purification. So if you remember, we were drawing entanglement wedges, which were glued together. So there's a very similar picture that we have for the canonical purification, where you take the legs at the extremal surfaces and glue them together. And that ends up giving you this a geometry that looks like this cylinder. And you could hope that if you compute the RT formula, you'll get these entanglement wedge cross-section cuts. However, the important point here is that one has the same tensor. So there's this T1 here and T1 dagger here, because you're taking two copies of the same density matrix and gluing them together. And so the RT formula is not assured. Like when we consider random tensor networks, we want independent random tensors at each location. And so it's not obvious that the RT formula can be applied to the situation where the tensors are correlated with each other. And this was what had led us to say that tripartite entanglement was crucial for holography, because certain kinds of tensor networks actually had only bipartite entanglement and they wouldn't have this RT formula. You can't apply this argument there. And the correlation between these tensors was sufficient to break down the RT formula. However, what we've showed here and what's true more generally is for random tensor networks, you can still apply this formula. So there was this understanding of random tensor networks as being related to fixed area states in gravity. And this was in a work a few years back with Chris Akers and also simultaneously by Dong, Harlow, and Marolf, where you consider states of gravity which are prepared by the path integral, but with specified areas instead of with specified area boundary conditions in the path integral, instead of providing smoothness in the bulk, which is what you usually do in the Hartle-Hawking prescription.
Right, sorry, Pratik, can I just ask a naive question?
Yeah,
I thought it was more. I thought these fixed area states were more like the perfect tensor states rather than random tensors.
Actually, they'll be very, what I want to argue here is that they'll be very closely related to these random tensor network states. So both the perfect tensor and the random tensor have this feature where they have a flat entanglement spectrum. And this is true of the fixed area states. So the fixed area states by construction has that feature, but there are more features of the random tensor networks which match the fixed area states, but they won't match the perfect tensors. Okay. So the random tensors are not exactly perfect, but they're close to perfect. And that's exactly what we'll see from this path.
Okay, so maybe we'll discuss this. Okay, thank you.
Yeah. Good. So here what we want to do, so here the way we defined this fixed area state was you have the usual asymptotic boundary conditions, but now you have an extra condition at the HRT surface gamma, which allows for a fixed area and an arbitrary opening angle. So with this, there's actually one-to-one connection between the random tensor network and the gravity path integral. So firstly, the simple connection is that you should think of a network as a discretized version of a geometry. But more so, there's a very nice connection between these two, because when you try to do the replica trick in the random tensor network, Haar averaging has this nice property where a Haar average over multiple copies effectively gives you a sum over permutations. So if you take n copies of the system, you'll end up getting something which is a sum over different ways to permute these systems. This is extremely analogous and in fact in one-to-one correspondence in some sense with the sum over topologies that one applies in the gravitational path integral. And each permutation can be thought of as one way to glue together the bulk saddles of fixed area surfaces. So when we take something like say trace rho cubed, which is this example, we have a gluing pattern which takes this slice to this one to this one, and this one to this one. This is exactly in one-to-one correspondence with the permutation that's applied in the random tensor network, which is this cyclic permutation. In this example, there are no more important saddles that show up, but if you have, say, multiple extremal surfaces and so on, there's actually a one-to-one map you can draw between different saddles in gravity and the different permutations that are important in the random tensor network. So in this sense, there's a very close connection between these two things. This is something that would not be true of the perfect tensor network or other things, other tensor networks. Okay. So now using that, let me just say we can do the same calculation for the reflected entropy by using the same replica trick and so on. It's a little more complicated with the tensor networks because you end up getting a sum. I mean, you have in a general tensor network, we have like many tensors at different locations, and we need to sum over all the different ways of gluing them together. It ends up being more complicated to resum. But we do have some qualitative picture for what happens. So we have a nice saddle point approximation that we can do. And the relevant saddles turn out to be the following. So firstly, here we are not doing the full resolvent trick. We're just computing the Renyi entropy at index n for the state that we already considered, which was rho to the m over 2. When we analytically continue m and n both to 1, then we end up getting the reflected entropy. Now, let's talk about this at just even integer m and integer n, where we can make sense of the saddles. There are two kinds of saddles. One is the disconnected one, which is the usual one we expected. But there's a slightly different saddle that we get for the connected phase. In the connected phase, what ends up happening is you don't get exactly the cross section. You actually get some sort of a pinched cross section. So you get a structure something like this, where these two domains are split by a pinched cross section. And there's a different saddle which fills in this region, which you can think of as some sort of replica symmetry breaking saddle. And that leads to the squeezing. When we analytically continue m and n to 1, what ends up happening is these points move outwards. And as n goes to 1, you end up getting the full cross section as you expect for the reflected entropy. So it's a nice way of understanding the bulk saddles that led to the original proposal. But more so, we have a prediction for what happens when you have a finite n. So the Renyi entropies would be computed by something like this pinched cross section.
Sorry, I have a quick question. What does it mean when you say as n goes to 1, this pinched thing grows? I mean, this is like, you can calculate this at integer n, right?
Yes.
I imagine.
Yes, that's right. So we can compute this at integer n. So for example, what you can do is just find what the location of these points is as a function of n. That is some analytic function. And then you can choose to analytically continue that.
I see.
Yeah. So we end up getting these squeezed cross sections, and it gives us something that's consistent with the proposal for the reflected entropy, and further motivates what to do with the Renyi version of the reflected entropy. Okay. So that's what we know about tensor networks. Let me just tell you one interesting feature that we learned from this, which maybe will give you a better picture for all the things I said. So a simple example we can look at is a single tensor, where we don't have all these features of the squeezing and so on. But this is a model that's very closely related to the West Coast model. In this model, we have these three legs, which have some bond dimensions, and there's a random tensor in the middle. This qualitatively represents a 3-boundary wormhole. So you have a 3-boundary wormhole with some open asymptotic boundaries here. And there are these horizons here, which are labeled in blue, the areas of the horizons are in one-to-one correspondence with the bond dimensions. So there's a map between the simple network and the multi-boundary wormhole. When we do the canonical purification, we effectively end up getting this following superposition. So we get a superposition between a geometry where we do the gluing at these locations, which was the disconnected entanglement wedge. That gives us these two disconnected cylinders. And we get another geometry, which is in the connected phase, where we glue at this location, which ends up giving this 4-boundary wormhole, which is connected. And now we can look at these two in the spectrum. This one, when we compute the entropy of A star, it's 0 because it's pure, it just purifies itself. So that corresponds to this sector. And the connected phase is this one, where we end up getting this, the answer, which is twice the entanglement wedge cross section, which comes from two possible RT surfaces here, either this surface or this surface. So it minimizes between the area of A star or B star. This is very similar to what we saw in the West Coast model. Now, this is the situation when we've considered that the only possible cross sections are these horizons itself. Like the single tensor has no information about anything in the middle. It's sort of a blob. Like we don't have any fine-grained information of that part of the geometry. So we were motivated to look at this in a little more detail. And one step you can consider is to split that tensor into two parts. So we have these two tensors. which are divided by an area which you can think of as this green surface. So this green surface is one possible entanglement wedge cross section that divides the connected entanglement wedge of A and B. Right? Good. So now what do we get? Now you can see that we can again do the same thing where we try to canonically purify the state and look at what the effective description is. The effective description is similar in the disconnected phase, it's the same thing. Now, when we glue together geometries at this location, we end up getting a single 4-boundary wormhole, which was the same picture as what we had before. And in this picture, it's clear that the entropy of AA star is given by 2 copies of this green surface. There's one here, and there's another one which fills in on the other side. So this is the natural saddle that corresponds to twice the entanglement wedge cross section. But there's actually many more geometries. So what one can do is take 2 of these geometries and glue them together at the horizons. If you do that, you end up again with a geometry which is a purification of the original one, but now it's a 4-boundary wormhole with genus 1. So this is a spatial genus 1. There's a hole in the middle. If you now look at the AA star, there's going to be 2 copies of the entanglement wedge here and 2 more here. So this is a saddle which gives rise to a reflected entropy that's 4 times the entanglement wedge cross section. And this was something that was missed in the original arguments. And this is something that we still don't have a perfectly good picture for in general, but this is something that we can see in numerics. So we can just consider a simple tensor network, which has these 2 tensors, and compute the reflected entropy of this model. When you do that, you find a spectrum which looks like this. So there's the usual pole, there's a mound of eigenvalues which corresponds to twice the entanglement wedge cross section, but there's many more. There's 4 times the entanglement wedge cross section, 6 times the entanglement wedge cross section, and so on. It's an infinite series in this genus expansion. It's a genus expansion in the number of holes in the spatial surface. And this is something we can see, and we can compute analytically the weights of each of these sectors, and it just so turns out that away from phase transitions, it's only either the disconnected phase or the connected phase that are important. But when you go near the phase transition, all of these become important, and they give important contributions near the phase transition. So this is something that, again, tensor networks have taught us. Okay. Good. Okay, so I think with that, I'd just like to conclude and just remind you that in this talk, I basically tried to motivate the holographic proposal, reflected entropy equals twice the entanglement wedge cross section, and showed it in some specific toy models and analyzed it a little bit more to understand phase transitions in it and other different features that are non-perturbative and were not understood before. And further, I'd like to say that we saw that random tensor networks here are great toy models for this replica trick. And this really should be explored more, and we should use it to understand different information measures because they have a very nice geometric picture. They correspond to these specific non-perturbative effects in the gravitational path integral, and they're also computable. And then finally, I tried to show you how by starting with these simple entanglement structures like the 3-boundary wormhole, which was a single random tensor, we can build up more and more complicated geometries, such as higher and higher genus 4-boundary wormholes. And we can keep repeating this process to get more and more complicated geometries. So this is sort of a step in the direction of understanding the emergence of geometry from some entanglement structure. There's a few generalizations to this story. You can consider these extra cross sections when you have islands. So in the East Coast model, for example, you can have island, and in order to compute the entanglement wedge, you get some cross section that lies in the middle of the island. This was something we analyzed in a paper with Ven Chandrasekharan, Masamichi Miyagi, and myself. And another generalization is to think about modular flow in this context. You can, instead of considering the canonically purified state, you can add in some modular flow. And in a previous paper with Rafael Busso, Ven Chandrasekaran, and Arvind Shabazi Mogadam, we had this proposal for the kink transform, which implements this modular flow. And so using that, you can probably understand something about how this flowed reflected entropy is computed by another bulk surface after implementing this kink transform. Okay, so with that, I'd like to conclude. Okay, thank you.
Thank you so much for the wonderful talk, Pratik. Are there questions?
Can I ask a naive question?
Yeah, sure.
So there was a study of classical correlations in entanglement wedge. And then, so this is done by Umemoto. And one of the statements in their work is that the transition point of the mutual information, let's say you have AB, subregion AB, and then you consider reflected entropy AB, like you did in this talk. And also let's consider mutual information between A and B. One of their claim is that the transition point of mutual information and entanglement wedge cross section does not match. Have you came across this kind of argument?
So transition point of what doesn't match?
The mutual information and reflected entropy.
It doesn't match?
So yeah, one of the claim in that paper was that that kind of thing. Have you came across this kind of argument?
I'm surprised that what we found in the model was even after including these non-perturbative effects, they were exactly at the same location.
Okay, I see.
So maybe I'll have to look at that paper. I'm not sure about this.
Yeah, thank you.
I think the claim is that, Pratik, the claim is that there is a geometric configuration such that what Keiichiro said is correct, which is a very surprising statement. So Umemoto claims that there is a particular geometric setup. So of course, if you take A and B to be disconnected, as you just drew, they both have a same transition at the same point, but one of them is discontinuous, the other one is continuous. These guys are saying that there's a particular geometric setup where this is true, which is surprising, but yeah.
Yeah, I'm surprised, but I'd like to look at this paper then. I don't know about it.
Okay. Thank you very much.
Okay. Thanks for telling me about that.
I do have a quick question just on this slide. What do you mean by rho AB half plus IS?
Yeah, I mean, what we're considering here was, it's literally like taking rho AB, the operator, and adding in this IS, and then thinking of it as a state. It's just a generalization of the canonical purification.
But it's not a state, right? You agree with that?
It is a state, I think. It is. Yeah, why not? I mean, we're considering.
It's like saying that take e to minus beta h and evolve that and replace it by e to minus beta plus ith.
Yes.
But that's not.
Yeah. But I mean, I think it's like we instead of this density matrix, we're considering this one.
Which is not a state, right?
And then interpreting it as the square root of this. This is the state.
I mean, the only thing I understand is like a cocycle. So there would exist a cocycle flowed state, but actually even the cocycle is a little bit icky because you need two states.
Yeah, the cocycle. So are you worried about like UV divergences or something?
No. I'm just saying that what is rho AB half plus IS?
Because I think otherwise this makes sense, right? Like we just it's the. I mean, I think you can think in the thermofield double. It'll be like taking the thermofield double and then evolving in time on one side. That's the state. Yeah.
So just one-sided modular flow.
It's one-sided modular.
Otherwise known as a cocycle. Yeah. Okay. Yeah.
Well, I thought for the cocycle you need to like do backwards modular flow with the other.
No,
like
that's full modular flow.
No, I mean like.
So what I'm saying is that if you take the cocycle with respect to the state that is identity.
Oh, with the state. Yeah, I see. Okay. Yeah, that's true.
Yeah. But that object is ill-defined in quantum field theory, but in quantum system, it is well-defined. Anyway.
Correct. That's right. Yeah.
Thank you.
Yeah.
Are there any other questions for Pratik? I do have one more question, and
Yeah.
feel free to just not answer it or not comment on it. This recent paper, the Markov gap paper of Hayden and friends,
Yeah.
they end with a paragraph or something about your paper, this what you're talking about, I believe. So what they say is this. They say that there is this Markov gap, which they take as evidence or a measure of tripartite entanglement, which they say, as was shown before by various people, I think Nazemi and Walter, that random stabilizer codes cannot accommodate for.
Yes.
Then they say, but there is work in progress, I guess, by you guys about random tensor networks.
Yes,
and the claim is that random tensor networks does provide potential, like enough tripartite entanglement to solve that problem. However, they continue to say that on your behalf that there are other problems. Is that would you clarify this cryptic comment?
I don't know what exactly they meant by that, because I mean, so if we just think about like time independent geometries, then I think what we've showed is the random tensor network has exactly the right kind of tripartite structure, so it's okay. Maybe there are other issues with tensor networks in the sense that, so when I talked about this fixed area state business, here there's an issue which is, like, if you consider these full tensor networks, which are hyperbolic tensor networks, it seems like you're fixing all areas simultaneously, and that's something you can't do in geometry. So I mean, in gravity, because like there's a non-zero commutator between them. That's the issue that needs to be resolved. But I don't think that has